Hello, good morning, everyone. I hope you're not tired yet. We still have some few more presentations to go. My name is Marco Bianchini. I'm a senior sustainability technologist at Lomartov as well, so it's a pleasure to be here, introducing you to the session number 3 of today's workshop. And after diving into the excellence of science, both from the OHPERA project and the invited speakers that delighted us now with these speeches, we move towards a new topic, which is not less important. Actually, it's a really important topic, discussing how we move from lab innovation to market. So to do so, we are going to get some speakers telling us how we can scale let's say the technology from a technical side. So for example, increasing the electrodes area, or how we actually bridge the gap between these technology readiness level increase and the market readiness level as well. So without further ado, I will introduce the first speakers. So let's welcome Blanca Méntrida. She's the head of innovation and business development and at the GreenRuptive Innovation Hub. She will tell us everything about it, so I won't spoil anything. With over 20 years of international experience, bridging research and industry to accelerate the deployment of clean energy solutions. So let's welcome Blanca. Blanca, sorry. Okay.
Thank you. Okay, hello. Thank you, Marco. Okay. Today, I would like to share how pilot-scale infrastructures can accelerate the transition from laboratory research to industrial deployment, particularly in renewable hydrogen and circular chemistry. So this is the context. Currently, we know that Europe delivers world-class scientific research, breakthrough laboratory results, advanced materials innovation. However, transforming all of these results into industrial deployment remains slow, risky. The challenge today is not invention, it's integration and scale. Our idea is GreenRuptive, the concept. GreenRuptive, what is GreenRuptive? GreenRuptive is a pilot-scale infrastructure created to accelerate the transition from laboratory research to industrial redeployment. It was launched by PTI Transcenter and UPV-CSIC with the support of the European Next Generation program. Our mission is very clear, is to reduce the scale-up gap in industrial decarbonization. We focus, because this is very huge, very general, and we focus in several areas. Main areas are the hydrogen technologies, in which we are speaking about in this event, CO2 valorization, circular chemistry based on biomass and waste streams. Our goal, our mission is not just research, but validate industry-ready solutions, economy viable. However, infrastructure alone is not enough. The key question is how to reduce the scale-up risk. GreenRuptive is located in the Paterna Technology Park. It's in Valencia, it's here. The hub includes 2,500 square meters of pilot-scale facilities and 1,500 square meters of innovation and office space. It's in the major and technological cluster, being surrounded by technological institutes and research centers that strengthen the collaboration and accelerates the industrial innovation. Regarding the infrastructure, what makes GreenRuptive different is not our equipment that is disruptive, but the integration of manufacturing, validation, pilot systems, and industrial utilities within a single site. Here you have a short video. This is one of our equipment. This is the furnaces area where we have more than 17. This is a coating device, a vacuum device. This is a Curionis, that is a spin-off. This is one of the pilots that I will explain after that. Another pilot, biorefinery. This is the Fisher chops that I will explain before, after that. Another pilot. This is our gases system. Balance of plant for electrolyzers, cryonics. Our laboratory for synthesis, that is totally new. We have also a clean room lab, characterization lab, with several metrology. Yeah, that's all. Okay. So, but beyond this physical infrastructure, GreenRuptive operates as an innovation ecosystem because we support collaborative R&D, accelerate technologies toward pilot validation, provide industrial integration and funding guidance, facilitate knowledge exchange across partners. Our collaboration model is flexible and tailored according to your needs, according to the needs of industry, researchers, and entrepreneurs. I will show you a few examples. This is one of our pilots in GreenRuptive. This is HIMET. This pilot comes from one European project. The industrial challenge of this project addresses to the steel mill scale waste. The challenge was how to decarbonize the steel mill waste. Okay, so what we did was to reduce the iron oxide with hydrogen, with green hydrogen. Okay, so we demonstrate the circular economy recovery combined with hydrogen integration. Another one was this one. This is Pfizer tropes. This is very advanced Pfizer tropes. And the industrial challenge in this case is this pilot addresses to the growing demand for sustainable aviation fuels. This is in order to valorize the CO2 to sustainable fuels, to the aviation fuels. Okay, so in this pilot, what we do is to convert the CO2 and hydrogen into fuels and chemicals. We have other several pilots, such as these other two are biorefineries. For instance, the left one is a biorefinery in which we convert biomass from hemicellulose into SAF or other aromatic hydrocarbons. In the right one is we convert biomass that comes from alcoholic waste into hydrogen and syngas that we use in the Fischer-Tropsch pilot to convert into fuels. Okay? Okay. But at the end of the day, pilot validation is essential, but it's not enough. It's not sufficient. We still face technical, financial, and regulatory barriers. What we need is to accelerate industrial deployment in Europe. What Europe needs is we need to share pilot scale infrastructure. We need we need mechanisms to risk sharing, and what Europe needs is accelerate industrial integration at a scale. From innovation to industrial integration at a scale is what we need. Okay, let's collaborate to accelerate Europe decarbonization transition. That's all. Thank you.
Thank you, Blanca.
Thank you.
Thank you. I think it was a great presentation. I think already highlighting some of the main challenges of scaling this deep technology to the market. It's a very capital intensive and very uncertain, let's say, sector. So this sort of shared infrastructure is definitely a great initiative to see, especially here in Valencia. So thank you for that. We move to the second speech of this session. So for that, I will invite Vicente Vert. He's a development project manager at MATTECO. He's also a startup based here in Valencia, so he will tell us all about it. And yes, so the speech, it's about electrodes and catalysts for alkaline-based water electrolysis from outer to large sheets. So let's welcome Vicente. Thank you very much. Big applause. And I'll take this.
Thank you. Thank you very much. Thank you for inviting us, Martov and OHPERA people, and you for waiting up till this late and to hear some people talking. So this is me, younger me, and that's okay. And I will just talk about, I will say something about MATTECO, of course, but also I will just try to explain how we can suffer coming from atoms to the large sheets that we are making electrodes, because MATTECO is making things like that. It's something electrodes and electrodes for alkaline and AM water electrolysis, both anodes and cathodes as well. So this is the starting point. And what I'm trying to explain, as I said before, is how we can just come from atoms within our MATTECO's catalyst into large sheets that will be something like 1.6 meters that was explained before, something like that for electrodes. So we need to come from atoms into this kind of black sheets. So then we need to pass through this kind of upscaling, of course, but also how we can just make it coating different catalysts and substrates. So let's start from the beginning, and the beginning is say why MATTECO is coming and we are making things from Valencia to the world. And this is because Our CTO is Gonzalo Avellán, and he's he's professor at the University of Valencia, and they developed the route to make LDHs based on nickel and iron. Of course, nickel is always present on this alkaline media for both electrodes, how we can just make it. And I would say it's a standard route and really upscalable route for making these things up to kilo scale. So this is the catalyst themselves, and the catalyst was really tested. Here appearing at different approaches. Of course, it's an LEDH. We are making some XFs and different deep tech analysis for the atom to really analyze what is behind the synthesis. And the synthesis that it is not because it's just an LDH, it's because it's something like clustered LDH. So then it means that allows to have some reduction on the oxygen evolution reaction better than a hydrothermal made before other routes that make that. So that's the key point. And that's the starting point for the MATTECO to grow and to stop as a company 2 years ago, just 2 years ago. As I said before, it's because it's clustered, it's because you have a good OER performance, so it's making more hydrogen with less energy, or I think the same hydrogen with the same energy, higher energy. So, is that thing. So, but this is not, this is atoms, this is powder. We can just make kilos of powder, it's okay. But then we need to put it in something else bigger. So then we start to making something, increasing the volume or increasing the size. This is what we started from. It is that shape, indeed. It's not so big. Because then we move to larger reactors. It's something like 10 kilos, 10 liters, whatever, doing so. But the idea for making as a company, we need to make it at larger scales, and we need to prove that they are larger scale. So then we are just having this kind of reactors, 10, 30, 400 liters for making these catalysts. But okay, it is a question that we can increase the volume. It's okay. It's, I would say, not really a problem. It is, but it's not so critical. But what about increasing in mass? So instead, we are just coming back to the initial small reactors that we have here, and we start from let's say 1 point, the standard reactor that we have, then increase 50 times the mass we are getting at the end. So we can perform the same synthesis using the same reactor, and okay, we are getting, of course, more mass of our catalyst. So that's meaning that we can upscale that production. It's okay. And then you can see something like from 3 to, let's say, 1 point whatever kilos at the end. We can just get at larger volumes. So, but they are really the same catalyst, and maybe it looks like they are not, or it is not. But if we go something in deep, we are just getting this kind of amount of their peaks for the X-ray diffraction. I will not go into details in the science. I'm sorry, I'm coming from industry. It's okay. But nevertheless, we are just saying that it's the same material at the end. Of course, it's not the same. It's something like clustered, smaller, more difficult to get. Maybe it is not exactly the same composition. So then it means that, okay, we are not having the same results at the end. So it's coming something that there are some limitations on the thermodynamics, kinetics, or whatever. So it means that we cannot rely on the same reactors. We are making more mass. So then, of course, if you remember that picture before, this is something like a magnetic steering over there. We can just make something like paddle steering, whatever, it's okay. We can just handle that. But if we are increasing the amount, they are changing from the chemical reaction. They are chemically engineering needs to apply. And then we need to replace something else with some more dedicated reactors with a proper design paddles, proper design, it's something like chilling. We need to control temperature. It is not the same to have this such amount of volume and you got this such a big amount. So we need to transfer that. So it is not straightforward to make, okay, bigger things are okay, but they need to be rethink on. So also it's happening the same. We have the catalyst, it's okay, we have the powder, we have the reaction, I would say, not the powder itself, because later I will explain that it's not so straightforward as well. But this catalyst needs to be applied on some surface to make an electrode, as far as we know. So for making electrodes, both for hydrogen production, CO2 reduction, whatever electrochemistry, photoelectrochemistry, it's okay. So then, we can just starting from this glassy carbon tip for making some rotatory disk electrode assessment. Also 3 electrode setups, something like 1 square centimeter, so really small, so really funny. And also we're increasing something like a single cells 5 square centimeters. Or remember that we need to move into let's say, 1.6 meters electrodes. Okay, we can replicate that models, we can replicate the values. I will not go into details in the electrochemistry. If you want later on, it's okay, but it's not the topic, I will say. But we can do so, and it's something like, okay, we can start with something like airbrush. It's okay for lab scale. Then we can move to a small automated spray coater, and then we can rely on commercial things. And commercial things exist, so then we can just move directly into a bigger machines. We can just have something like 0.5 meter times 0.5 meter. It's not be a problem regarding the technology. Maybe time consuming. It's okay, it's larger surface. But maybe other issues we need to take into account. Please notice that kind of spot over there. Then we need to start relying on something like ATIC, something explosion, something like we are using alcohols or whatever. It's not the same to have this kind of amount to bigger amounts, concentration. So, hey, let's have a look. It's not straightforward as well. It's something lab scale, it's something industrial scale. Safety plays a role over there, so we need to think about that. And the same happens when we're just making this, I would say, inks in that part. We can start something like ultrasonic probe is okay. Then we have something more elaborated. But then we start facing some problems because we need to have more time, because we have more volume. So then it's something like, hey, it becomes hot. So what we can just do, we can add this cooling system, fancy cooling system with ice. Okay, it's okay, but it's not really good for me in an industry. So at an industry, we need to think in other things. Something like bigger vessels, we have something like chiller inside, how we can protect and control the temperature. But wait, the same happens with all the supplies that we have here. Water needs to be something like in a pipes. That could be something like avoiding explosions as well, because we are dealing with alcohols. So there are something ancillary things that we need to think on better than something like bigger volumes or made of stainless steel or whatever. So just, for you to have a look and remember what happens. And also, as I said before, it's not straightforward to make something like powder, because when you have a reaction in water, they need to separate somehow the powder. It's okay, a centrifuge. Well, let's make it bigger. Well, not so bad. We can just, 3 times washing, 3 times centrifugation. Well, not so bad. But let's think about 400 liters. 400 liters cannot be done in such a small machine. So you need to rethink another one. What kind of centrifuge are you using? What kind of separator, filtering? So it is a question that needs to be something like chemical engineering and also recirculating, and I need to put it again in a vessel, whatever. It's not so, I would say, easy to put something like the same bigger. It's not really working. Not all the time. So I would say, well, maybe once. Okay. So, let's say that. So we are making powder catalyst, no straightforward, but we can do so. We can also this stable catalyst suspension. I need to talk something about MATTECO, how good our catalyst is. So this is something the commercial. And of course, but the good thing is that we can make it in the water suspension. So it's a question that we are not using this kind of, I would say, complicated solvents, whatever, afterwards. But hey, it's nickel-based, so it's a question of safety. Also, we need to rethink on that. It's not straightforward to make such amount of things on nickel on a lab scale, but if you have tons of material made of nickel, hey, you need to think something about safety, about something like equipment for your safety yourself, the facilities, then you need to regenerate the air and whatever. It's not, I would say, easy. It's not cheap, so just need to think on that as well. So at the end, yes, we have the catalyst and we have this kind of small things. It's a 3-tool setup, something like for testing, some companies. By the way, we need to start growing that, and things like that is 1.6. What we are saying, hey, it's not so straightforward. We cannot put it on the same whatever we have, machine, roll to roll or whatever. Hey, just think on the machine we need to do this material too. So it is a question that we do, and also we are also developing some other techniques for coating over material, not only directly on inks or painting. We are making a direct growth of our material within the substrate. So then here you can see some scanning electron microscope pictures when we can see that there are some plain materials, respectively they are felts, foams, fibers. We can just grow our catalyst over there, chemically bonded to our material, so then we can just make it a different approach. So then the reactors are different that we are just thinking on. So just some pictures about how our material performs in a single cell. This is something like on your left-hand side is something like a oxygen evolution reaction in a single cell, and on the right-hand side is a cathode made as 3-electrode setup, so that we can just see that we overperform. Sometimes platinum, not really good at the end, so because of alkaline, whatever, so it's a question of values for you to know. So what we get for as a lessons learned, you need to have space. If you are playing with things that big, you need big machines to do so, and you need big place for traveling, handling, whatever. So take care of that. And also, I mean, it's okay to make the first jump from lab to one commercial but then think on the bigger things, because not all the machinery are big enough or really tailored for you or so easy. So it's something lead times. It's something like 6-9 months, 1 year, 1 year and a half. Hey, think on that. And of course, if you can learn from other processes, please use it. So it's my recommendation. I mean, don't try to invent all the times the wheel. There are some things that are invented, so just use them out. We are innovation. On the first talk, so innovation is something, and technology. Use technology for your application. And of course, define the process and really understand what the customer needs, because depending on the size, you need to define what you are doing. And of course, have a nice team and have a nice funding. So this is what I'm just acknowledging here. This is the teams and the fundings and whatever. So, gracias, and thank you very much.
Thank you very much, Vicente. I think it was also very, very interesting presentation, showcasing a bit of the challenges from scaling the technology to higher TRL and higher scale. And I think you also mentioned in the last slide something I used to connect to our next speaker is understanding your customers' needs as well. So it is really important that when we work on innovation, we do so aiming at solving some problem, or someone has to be experiencing that problem. We need to fully understand those problems in order to successfully transfer, let's say, innovation to the market. So for this now, I will invite our next speaker, Istvan Burus from eChemicles, also part of the OHPERA network, and he'll tell us more about business ideation, innovation tools for early stage innovation. So thank you very much. Let's welcome Istvan.
Thank you, Marco. So what I want to talk to you about now is a small project that we are doing at eChemicles called Evolute. This is a so-called EIC booster project. These are very small projects for EIC beneficiaries for solving challenges in a very targeted way that come about when you are doing your main project, and you get some small funding and some time to work on these challenges or critical aspects. So this project just started, and we will finish it by May. And the goal of the project is to carry out an evaluation of the available business ideation tools and to provide practical guidelines for low TRL projects about them. And because of the portfolio that was mentioned a lot, I don't know if Johannes is still with us, but we have a specific focus on these EIC project portfolios, so on these areas dealing with renewable fuels and chemicals. So I will not talk about eChemicals too long, because my colleague Csaba will have a dedicated presentation about our company. But a few words about why we think we are well suited to do this small project. So our team had carried out a successful up-to-tech transition of a CO2 electrolyzer technology, and now we have all the commercial partnerships for proper commercial development. And it's probably a success story of European funding in the way that it started out as an ERC starting grant, then a proof of concept, an EIC transition project, and just last week it was announced that we will receive the EIC accelerator funding as well. And this is crucial because you see that it took 10 years for us to get here. And we are still not entirely on the market. We have some commercial pilots starting with our containerized system. But you see that this is it takes a long time, and I think that we are fast, and still it takes a lot of time. And because of this experience, we are often invited to, for instance, Pathfinder projects and transition projects to help with the commercial strategy. And we can do this because our team combines both scientific and engineering excellence and business and project management expertise. So we understand the very specific challenges of low TRL and long time to market projects. So what is the need? The need is what was mentioned in Johannes' presentation, this European paradox, so that Europe really struggles to turn scientific research into commercially successful businesses. And this is what the EIC is trying to change. So to shift the focus first from discovery to invention, and then from invention to innovation. So because of this, EIC projects are expected to apply business logic already at very low tier levels. And because of this, researchers and project partners are encouraged to use these kind of business ideation tools like the business model canvas, SWOT analysis, and so on. However, there's a problem. The problem is that most of these business ideation tools were designed in the context of much faster product development. Mainly in the US, in the software domain, where you can have minimal viable products and so on. It's very difficult to imagine in the hydrogen space minimal viable products like in some software. So the direct application of these tools can be very limited for deep tech projects, because they are facing a lot of moving parts. Market uncertainty, technological uncertainty. In these low tier levels, you are very much before actual product development. And of course, you have a very long development horizon. So because of this, if you do not really have the proper facts to work with, these business analysis exercises can become really formulaic. So not substantial, but just to do it because you have to do it. And still these early results of these assessments can get burnt in, with which I mean that project participants start to treat these results as facts, and it's easier to return to these early results than to start from the scratch, even when you know that it's no longer really applicable. So, and there's a lot of frustration and also skepticism by the researchers who are trying to use these tools. It's just an accident that I'm looking at you, Sixto. And it can be very difficult to grasp and communicate the actual potential of these projects because of this mismatch of the available tools. So what we are trying to do here is to provide these low-tier deep tech projects with a business ideation toolkit that they can actually use. So they can better articulate and communicate their project results and the promise of their projects. And in the end, we think that this can very much improve the commercialization potential of these projects if they are using the right tools. So, as I mentioned, we are early on in this work, and it's important to understand that we do not want to create whole new tools. We want to understand, also talking to researchers and also startup companies, we try to understand together with them which tools actually work in these low TRL projects. And some of the promising examples that probably can be very useful in this is the innovation readiness concept of KTH, Stockholm. I think a great advantage of this concept is that they provide realistic business ideation targets for each of the TRLs. So the idea there is to keep your market readiness and business readiness in line with your technological readiness progress. So it doesn't expect you to do very high level business ideation and business strategy development if you are at TRL 2 or TRL 3, but it gives you some realistic targets of what you should achieve by TRL 2 and TRL 3, for instance, in terms of these business ideas. And the other one is the impact canvas, where a big advantage is that it's suitable for high uncertainty environments, and also it focuses on the broader societal value of the concepts and projects, so you do not have to think about immediate commercial exploitation. And it's I think it's not a coincidence that obviously the KTH is Stockholm. The impact canvas was I always forget whether it was Tampere or Turku, but some of the Finnish universities. So both of these tools are from Northern European countries. I think it's not a coincidence. I think they are doing much better in this context than other parts of Europe. So yeah, what's next for us? So we are, as I told, doing a critical review of these available tools. We will also do a survey of innovation managers of EIC projects to understand what their experience is with these tools, and then we are going to analyze and adapt these tools to low TRL level projects. Of course, then we will pilot the selected tools on a concrete research project, at least one concrete research project, and then we will finalize this toolkit and make it available for European projects. And in case you are familiar with some of the problems that I discussed, and you will like to discuss these further with us, your experience or your ideas about this, we will be very happy to hear from you. So, thank you.
Thank you very much, Istvan. I think it was a great conclusion of this session related to upscaling lab technologies to market scale. So I think now to going forward, okay, so yeah, first we move to our beloved Slido. So just take your time to scan the code. We have one question for you at the light of what we discussed in this session. Yeah, here you go. The question is, what would make you feel more confident in these technologies? You know, after what we've discussed so far at the light of these speeches, what do you think? Yeah, of course, all these points are definitely relevant. It seems we have two champions so far, proving large-scale industrial projects in operations and the piloting, and that providing evidence that the green hydrogen can be economically competitive. That's always, I think it's a common problem in many technologies when we compare to the conventional technologies, right? To be economically competitive. Then on the policy side, and having clear regulation, long-term policy commitments, supporting market upscaling. Apparently, we have less interest on the environmental impact assessments, and the better public information and education about hydrogen technologies that could usually foster the technology acceptance. That's also that's an important topic. But yeah, I think we have a winner. Yeah, we do have a winner. So apparently, proving the large-scale feasibility of these industrial projects is definitely one of the biggest point to address, to increase the confidence to these technologies. So yeah, thank you very much for your answers. Before moving to the next steps, I would open the floor to any questions from the public, from home. Yes, Sixto, do we have microphones?
Thank you very much. Yeah, I have a question for Blanca. Yeah, thank you very much for your great talk. You showed like very amazing facilities and projects that can be developed there. But what is the way that, for example, one team can try to test their concept in your facilities? What is the way that we should approach for this?
Step is we need to know what are your needs, and we need to study what are your needs in terms of if you need technical support, your space, if you need to use some of our equipment or pilots or whatever, because we have pilots, we have equipment, we have different facilities. So once we study your needs, we provide you the budget of this case. Of course, we need to be aware about the timing of the project, of your project. Okay. So, for instance, nowadays there is a company that is installing his lab in our facilities. They are going to use the space, and also, according to the contract, they are free to use our manufacturing, the synthesis lab, and also the characterization lab. Both labs are included in the contract, are free of use. Okay. Of course, we guarantee the confidentiality of each project, and you can also share your results if you want to share your results, or you want to share with other colleagues the results, because it's an open ecosystem, it's an open innovation ecosystem. If you want also to rent offices, we have a lot of offices to use. Adding to that, we have workshops and training courses to use different equipments, because we have so many breakthrough technologies to use. Deposition coating machines, vacuum coating machines, so many. So I invite you to visit our facilities, because you are in Castellón.
Yeah.
So it makes sense to visit our facilities in Paterna, of course. So please. Okay.
Any other question? I have a question from Chava.
Yes, but for the people online, it will be hard to hear you. Sorry.
No, thank you. So also to Blanca, that first project was very interesting regarding the direct reduction of ore using hydrogen. So it's a small blast furnace, basically, what you have?
It's a small?
Blast furnace. So you have the ore melted, yes, and then you inject the hydrogen.
Yeah. It's a tower of, imagine, 5 meters of height, and we introduce nowadays 500 tons per year of iron oxides, and we reduce the iron oxides to iron metallic. Nowadays, in the siderurgic sector, they reduce the oxide, iron oxide with carbon, and they produce a lot of carbon dioxide. So with this technology, we reduce the iron oxide with hydrogen. So it's super. It's circular economy. Okay. It's fantastic.
All right, thank you. Any more questions? No questions from home? Yes, we have.
It's just to ask you, Vicente, which is, I've seen your challenges, but I would like to have the number of your production rate of the electrocatalyst. If you can say, tell us something about that. Yeah,
You mean how many tons we can produce?
Yeah, I'm curious.
Well, nowadays we are not producing such a big because we are not such a demand. I mean, the customers are not willing to have such amounts. But our capacity is something like we have with the 400 liters of a reactor, 400 liters, that is something like it takes one day. We can produce per day something like 20 kilos per day. So then, I mean, depending on how many days we need to produce, but it's something like that. But this is only for the anode catalyst, but also we are producing the cathode as well. It's a different technique of doing so it depends on facilities, but nowadays we can produce sheets up to 1.5 times 1.5 meters of electrodes, so we can code that size. So, I mean, you're welcome.
Okay, thank you very much. If there are no more questions, neither from home, I think we can move. So I'll invite to the floor my colleague Mihaela. There we go.
Yes, for me it will be very, very brief because now it's a very interesting part that is next, which is our lunch. We feel sorry for the people at home that they cannot enjoy neither the food, neither the networking with us. So next time, feel motivated to come and join us in our workshops. But before going to lunch and making sure that we still keep your attention, and we will see you after the break as well, I remind you again about our innovation workshop under the HYPER project dedicated to liquid organic hydrogen carriers and in their relationship and acceptance, the stakeholder needs and the concerns. So we will be discussing about this on the 3rd of June, and will happen also online. So you can follow us there and contribute. And then I will show you briefly a surprise that we are having for you. Meaning that while you were presenting and talking and asking and so on, we have here an artist with us. Fanny is drawing everything that we are discussing, and will be presenting at the end of the day a graph, a visual of everything that happened during the day. We can briefly show you how it looks so far, just to make sure that we still keep your attention. And you will join us also after the break when we will continue our discussion, and she will continue to draw. So we will be able to see at the end of the day where are we, where we want to be, and how this can be presented to general public in a not very complicated way, but motivating one, so we can also get their support and understanding. And now it is time to go to lunch. We will have 1 hour break with all the others and also us. We will meet at 2:30 CET, so please come back, enjoy your meal. And for the ones here, enjoy your networking also.